Why does this work? So we're going to do another proof of correctness, and it turns out that the same strategy that we used for naive is going to work out really well here. In particular, what holds is that the product of A and B is always equal to the product of x and y plus z. And again, since x is going to be counting down and eventually reach 0, z is going to ultimately have to hold the product of A and B. Can we prove that this is the case? Again, we need to do two things. We need to say that it starts off with that being the case. And that's the same exact argument that we had in the naive algorithm, because x starts out as A, y starts out as B, and z starts out as 0. So that holds. And now we need to show that if this condition holds at the beginning of the top of a while loop, then it's going to hold at the end with the new values of x, y, and z. So let's remind ourselves how x, y, and z change in the while loop so we can see whether the condition still holds. And we're going to have to break this into two cases. First, if x is odd, and second, if x is even, because two slightly different things happen. So in the case when x is odd, the first thing we do is add z and y together, make that the new value of z. Then we do a bit shift on x, which in this case is equivalent to subtracting 1 to make it even and smaller, then halving it, and y, meanwhile, gets doubled. So what can we say about x prime times y prime plus z prime, so that is at the bottom of the loop? So we can substitute in these values, get x minus 1 over 2 times the new value of y, which is 2y, plus the new value of z, which is z plus y. And we notice that this 2 and that 2 cancel, and we get xy minus y plus z plus y. And again, the plus y and the minus y cancel, and we do indeed get xy minus z, which we had assumed holds in advance. So that's a times b. What about the case where x is even? So in some ways this case is easier because the bit shift on x just halves it. Z doesn't change at all, and y again is doubled. Let's look to see what happens in this case. So what happens now is the value of z doesn't change at all, and in some sense, x and y just move a 2 around. So x gets halved and y get doubled. When we multiply those two together, they cancel. And again, we get xy plus z, which we had assumed coming into this is equal to a times b. So the new values of x, y, and z, in either the case where x is odd or x is even, continue to satisfy this property. So this is kind of strange. What it's doing here is we're moving a factor of 2 back and forth between x and y, actually generally from x to y. And whenever it's odd, and we have to shift x a little bit more than that to make it balance, we move some of the value into z. So this is kind of wacky.